Okay guys, so one of the many lessons we need to cover is factors that speed up the rate of reactions. This will actually be a huge lesson in AP chemistry. It's actually called kinetics. Very important concept. For what you need to know, you just need to know a couple of the factors. At the end of this little lesson, I'm going to show you a quick little video that's actually really funny, well, funny to me. And it also goes through and talks about the factors we have to know, plus a couple of more that you'll learn next year. So it should give you a little synopsis of what we run through here. But what we're, again, talking about is how fast reactions are going to happen, and maybe not how fast they're going to happen, but what will cause them to happen faster. Okay, so let's go ahead and start. So you should write in your notebook rate of reactions. The dissolving process, you don't really need to write that. I just want to show you a quick little animation that's going to walk through what happens when you put something like table salt or any ionic salt into water, what's actually occurring. So let's go ahead and take a peek at this. It's going to talk as well, so we'll listen to that, and then I'll add what I need to add too.
Let's add a small amount of table salt, sodium chloride, to water. As you know, sodium chloride dissolves in water. Click on the zoom button to view sodium chloride dissolving in water on a microscopic scale.
Okay, so before I click zoom, we have put the salt in there. We all know when we put salt or sugar or whatever into water that we can't actually see it anymore, that it dissolves. But ionic substances do something special on a microscopic level.
Polar water molecules interact with the positive and negative ions of a salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between the water and the salt ions causes a salt to break apart or dissolve in water.
So you see here that water has a part, this little weird squiggly sign means partial. So it has a partial negative end and a partial positive end, the polar ends of the molecule. And so if it wants to steal the chlorine off of this big clump, the positive end goes and steals it. If it wants to steal the positive end, the negative end of the molecule goes and grabs it. So that's how it actually pulls it apart. And it pulls it apart, it still has its same characteristics, its same properties, but it's allowing it to be pulled into small enough pieces that we can't see it anymore, which is why we are visually not able to see it, but it actually does exist. All right, so let's go ahead. The 4 ways that you are going to be responsible for, and again, the video is going to show a couple more, but the 4 ways you're responsible for are if we increase the temperature. So if we're trying to dissolve salt in water, if the water's hot, it'll dissolve faster. And I think most of you probably know that just from experience, but we'll talk about that. Grinding up of the solute, so putting the solute into smaller pieces. So for example, using regular table salt instead of rock salt, which are those big chunks of salt. Stirring it while it's trying to dissolve helps. And adding a catalyst. So those are the 4 that we are going to look at. If you're still writing them down, go ahead and pause. Once you're done, you can continue. So temperature's effect. Temperature has an effect because in order for that water molecule to have come over and taken the plus or the minus off of that big chunk, it has to travel there. If it's moving faster, it can travel there faster, pull it away faster, come back and get another one, pull it away, come back and get another one. The more average kinetic energy you have, the more that solvent is going to be able to come over and pull that solute apart. So that's why temperature has an effect on the rate of a reaction, is because it will allow the particles to interact with each other more quickly. In terms of grinding it up, if you think about a big clump like rock salt, the salt that's trapped on the inside of that big clump isn't coming into contact with the solvent, and in order to dissolve, it has to be in contact. So if you take a big chunk of salt and you grind it up into a fine powder, all of a sudden all the interactions can occur. So grinding is going to increase the surface area, and because the surface area is increased, now the particles of solvent can come into contact with the particles of the solute. They'll use a really nice example in the video that you're going to watch of this, and I think it's funny, but again, it really shows you that how the inside of the big chunk doesn't even come into contact, so it can't be reacting. Then we have stirring. Now stirring, of course, is going to not only stop your solute from just hitting the bottom of the container. If it hits the bottom of the container, obviously only the top of it can interact, but it'll also get the particles moving around, getting all the solvent that's possible to be able to come and interact. with that solute. So by stirring, you're moving the solvent so that it can attach itself to a solute ion. Please don't think that by stirring, you're speeding up the particles, though, because temperature is the only thing that can give the particles more energy. You're simply distributing the solute throughout the solvent by stirring it. And then we have a catalyst. Biology class, you probably learned about catalysts. Catalysts are defined as something that will speed up the rate of a reaction, but they do it, I want you to understand why, they do it by giving the reaction a different way to occur. So it actually gives the reaction another way to happen that's faster than what the original way was. Okay, and again, the video has a funny example of that as well. Some examples of catalysts, you probably saw enzymes when you're in biology class. We have chemical catalysts, so we have substances we can add that actually will change the reaction's rate, but doesn't change anything else. Still have the same reactants and products, it just changes how fast it happens. Sunlight is often a catalyst. If you have hydrogen peroxide at home, you know that it's in a dark brown bottle because sunlight is a catalyst for decomposing that hydrogen peroxide. Okay, so that's your catalysts. Now let me go to our video. So I want you to watch this video. You don't have to take notes on it or anything, but again, I think it's going to give you a good demonstration or a good example of what is occurring. I'm going to be playing it. If it's hard to hear out of here, you can always search on YouTube, TED, T-E-D, and then rates of reactions. You'll see the title of it here, and you can watch it. It's just 5 minutes.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk to her class. You'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. Collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I proposed 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I proposed that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help ensure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? And a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
All right, so again, I think it does a good job of kind of showing you those different concepts. All right, we will see you in a few days.